So now we've talked about space a bunch. We've talked about things that are in space, different objects that are out there. We've talked about stars and how stars are born, they live, and then they die. And now we need to talk about light. The reason that we need to talk about light is because light is how we know everything about space. Because we can't go to a star. We can't even go to the sun, which is the closest star to us, because we would burn. So the only way that we can know about stuff that's out in space is by the light that they are giving off. By the end of today, there are a couple things that you should know about light. The first thing is that you should be able to describe how we are able to see light. Like, what is light even? It's something we're so familiar with, you probably haven't thought about it too much. You should also be able to identify the electromagnetic spectrum. It's a scary looking word, but your target for today is just to be able to point to it and say that is the electromagnetic spectrum. And then you also should be able to talk about how the light that we are able to see is only a really small piece of that electromagnetic spectrum. So before we can really get into light, electromagnetic spectrum, and space, we need to talk about how can you actually see light? What is actually happening? So, photons is a new vocab word, photon. Notice that it has the word photo in it, and photo means light. So, photons are basically little balls of energy. You can't see them necessarily like the ball piece, but just know that photons are little pieces of energy. And what happens is anything that gives off light is giving off photons. So the sun is giving off photons, stars are giving off photons, the lights in your house, the light from your computer, everything that you can see light. When it turns on or when you can see the light from it, what it's doing is it is shooting off these things called photons, and it's just energy. So it's shooting off all these photons, and what happens is that the photons, they move. They go from the sun, they fly through the air, and they land on your eyeball. Photons come out of the flashlight, they fly through the air, and they hit your eyeball. So when you see light, what you're actually seeing are all these photons slamming into your eyeballs. So right now, there are photons coming from everywhere, from my computer, from the sun, the light that's on over there. There are just all these photons that are bombarding my eyeballs. And when a photon hits my eyeball, I say, oh, look, that light is on. Or, oh, look, the sun is out. At nighttime, when there is no sun, the photons aren't hitting our eyeballs, and so we're saying, oh, it's dark outside. So when you see light, what you are actually seeing are these little things called photons that are banging into your eyes. So now that we understand what a photon is and that a photon is actually moving from the source to your eyeball, we can talk about what a light year is. So you've probably heard of a light year before, like Buzz Lightyear, or maybe in like Star Wars or something, you've heard about something being light years away, or I don't know. You've probably heard of something called a light year before. And what a light year is actually a distance. So that's kind of hard to wrap our head around because when we think of a year, we think of it as being an amount of time, right? It's 1 year from one birthday to the next birthday. It's amount of time that's going to pass is 1 year, or maybe 5 years is going to pass. But in the space, a light year is actually a distance. It's like a mile or an inch. So instead of being 1 inch or 1 foot, it is 1 light year. Okay. So a mile is written on this slide here is 5,280 feet. That's how big a mile is. Just like this is 2 inches. Okay. The distance that a light year is is the distance that light, or those photons, will travel in 1 year at the speed of light. What? That doesn't even make any sense. So a light year, I'm going to say it again, is the distance that those photons will travel in 1 year at the speed of light. So it's really hard for us to wrap our head around this, because if I turn on a light switch, the photons go from the light into my eyeball instantly. It doesn't seem like it takes time to do that, but it actually does. It's just instant. It's just really, really fast. But light that is being put out by stars and stuff, that light has to travel all the way through space and hit your eyeball. So these photons, they are traveling at the speed of light, and a light year is the distance that they will travel in 1 year. So let me explain this a little bit more. So if a star is 20,000 light years away, let's say, that means that the photons that were shot out from that star, they have been flying through space at the speed of light, which is the fastest thing that we know. They have been traveling for 20,000 years before they hit your eyeball. So if I say that a star is 5 light years away, that means that the light has been traveling for 5 years at the speed of light before it hits your eyeball, and you say, oh, look, there's a star. I know this is hard to wrap your head around, because normally when we see light, it's just there and it's instant. And when you turn on a flashlight, it's instant. But that's because you are so close to it. So when we see light from stars, we are actually seeing light that they gave off a long time ago. We are seeing the photons from a long time ago. So if a star is 5 light years away, the star gave off photons, and for 5 years, those photons have been flying through space before they hit your eyeball. Crazy. Okay, so this picture this little cartoon says the light from distant galaxies can take millions of years to reach Earth. So they are millions of light years away, which means that the light has been traveling for millions of years before it falls and hits your eyeball. And then they say, talk about long time no see. Seriously, because that's millions of years. That means that the star gave off photons that you are seeing before you were even born. Some of the photons that the stars are giving off were given off when the dinosaurs were alive, and they are just landing here on Earth. Crazy. So I realized that you couldn't actually see the cartoon because my picture was in the way. So I just added it here, so hopefully you can see it again. So to read it again, the joke is the light from distant galaxies can take millions of years to reach Earth. Talk about long time no see. Okay, so now we can talk about how far away are things that we are familiar with. So here's Luna, the moon, which is a natural satellite to Earth. And the moon is the closest thing in space to us. But obviously, we would not think that the moon is like that close, but it is the closest thing to us here on Earth. So how many light years away? Because remember that a light year is a distance. It's like a mile. So how many light years away is the moon? The answer that the moon is 1.3 light seconds away. It's a weird thing to think about, but that is a distance. 1.3 light seconds is a distance. So if we think about that, when the photons that are on the moon finally reach our eyeballs, how long has it taken? It's taken 1.3 seconds. So if a photon comes off the moon, it takes 1.3 seconds to reach your eyeball. So if you look at the moon tonight, what you are seeing is light that actually is 1.3 seconds old. Okay, it'll get a little less confusing when we get away from seconds. Okay, so here's the sun. So how many light years away is the sun? This one you may have heard of before, but you might not have understood why we see the light from the sun later on. Now you do, because you know that it's photons and they take a little bit of time to get here. So the sun is not so far away from us in space. So how many light years away is the sun? It is 8 light minutes. That means that the photons that are given off from the sun take 8 minutes to get here. So if you look outside and you see the sunlight, which hopefully you're doing this during the day, that sunlight was actually given off 8 minutes ago. It's old sunlight. All right, here's Pluto, that is pretty far away, Miss Keenhold. Like that's, on the outer edge of the solar system. But it's only 4.6 light hours. So we're not even at a light day yet. It doesn't even take 1 day for the light from Pluto to get to us. It only takes 4.6 hours. So these things are actually super, super, super close. We're not at a light day or a light year or a light month or definitely not a light year yet. Okay, so how about the closest star to us? We know that the sun is the closest star to Earth because it's in our solar system. But what is the closest star that's not the sun? So here is the sun. It's right in the middle. The Oort cloud is basically the outer edge of our solar system. This is 2 light years. This is 4 light years. So the closest star to us is either Alpha Centauri or Proxima Centauri, these two over here. And they are they're about 4 light years away. So the closest star to us, apart from the sun, it takes 4 years for their light to come and hit your eyeball. And that's the closest star. Think about all the billions of other stars in our galaxy and the billions of galaxies that exist that are way further away. This stuff makes me super excited. So the closest star to us is 4 light years away. Remember, it's a distance. So it takes 4 years for that light to hit your eyeball. All right, so now what about the Milky Way galaxy? So if you are looking at this picture, you can see that the sun's orbit is kind of like a light yellowish color, kind of like halfway through the Milky Way. So that's how the sun goes around the Milky Way. It is in the middle of the Milky Way. It is 27,000 light years for us to get to the center of the Milky Way. And remember, in the center of the Milky Way, there's a giant black hole. Okay, so 27,000 light years. So that means that even though there's no light in the black hole, if there was, it would take 27,000 years for the light to get from there to your eyeball. That's insane. And then if we're talking about how big the Milky Way is across, it's 100,000 light years from one side to the other side of the Milky Way. So if you were on one edge of the Milky Way looking at the other edge of the Milky Way and you could see a star from there, the light would be 100,000 years old. You couldn't ever, even if you could travel at the speed of light, which we humans can't do, nothing can except for photons. If you could travel at the speed of light, you would have to live for 100,000 years to get across the Milky Way. This stuff just blows my mind. I'm excited here, but I just think this stuff is so cool. Okay, so we've now talked about how Earth and we've talked about the solar system, how far away the sun and Pluto is. Then we just talked about the galaxy that we are in. But we can also see other galaxies. There are thousands, millions of other galaxies out there. Okay. The closest one to us, so if we're here, it's right over here. The closest galaxy is called the Andromeda Galaxy. And it's called Andromeda because that's a constellation. And if you look towards the Andromeda constellation, you can see this galaxy if you know what you're looking for. So that is the closest galaxy to us. Really, really, really close in terms of galaxies. It is 2.5 million light years away. That means that it took, if the stars shined their photons, it has taken 2.5 million years for those photons to get to Earth. That is crazy. Are you ready to be blown a little bit more? And don't worry, I understand this is crazy stuff. It's really hard to wrap your head around. But I just get so excited about it. So if the Andromeda Galaxy, if there were people or aliens living on the Andromeda Galaxy right now, okay, and we are living here, obviously, right now, but we are 2.5 million light years away from each other. That means that the light has taken 2.5 million years to get across. So if they were looking at us, they would see the light that the Earth gave off 2.5 million years ago. 2.5 million years ago, there weren't any people on the planet. There were just our ape ancestors. So if for some reason the Andromeda Galaxy was able to look at Earth and there were people or aliens living over there and they were able to see us, they wouldn't actually even see us. They would see 2.5 million years ago. It's like a time machine if you were able to see that far. That probably blew your mind. You probably don't understand it, but it's just so cool. There are billions of other galaxies. The Andromeda one is the closest. Space is absolutely gigantic. Something that I really like to think about is this is the constellation Orion. And in the constellation Orion, there's a star called Betelgeuse. And it's that top left shoulder there. And Betelgeuse, if you're looking at it, you'll probably notice that it's kind of like an orangey reddy color. That's because it's a super red giant. So if you think about the stages of the star, stellar nebula, main sequence star, red supergiant. So this thing is actually starting to die, right? It's used up all of its hydrogen. It's starting to fuse heliums together to make carbon, and it will keep going all the way to iron because this is a huge star. Okay. Betelgeuse is 640 light years away from Earth, which means that if you go outside tonight and you could see Betelgeuse, you would actually be seeing light that was shined 640 years ago. Now, Betelgeuse is a super red giant. So what stage is going to be coming after the super red giant phase? The supernova phase. Betelgeuse is 640 light years away. Do you think it is possible that Betelgeuse has already exploded in a supernova, but we just haven't seen it yet? If Betelgeuse exploded today, it would take 640 years for us to look up and see the photons from the supernova and say, oh, look, Betelgeuse exploded. So I think it is so crazy to look up at stars, especially ones that are super red giants, and say, I wonder if that star even exists anymore because that light is so old. So I'd like to take a minute and give you a second to really digest everything that I just told you, because that was a lot of information. It's kind of weird information. It's the kind of information that really kind of blows your mind and makes my brain hurt, and I understand it. So I want you to take a second to reflect on kind of how you're feeling and really try to wrap your head around everything that you just learned. I only have a little bit more mind-blowing information and new information for you today, and I just want to include it on this presentation because we're going to be talking about this for the next couple of days. So I want you to hear my voice explaining it. So this is the electromagnetic spectrum. And what I'd like for you to do before I explain it to you at all is I want you to take a minute or two, pause me, and make an observation or make two observations about what you notice in this diagram. So really look at it and make some observations. Giving you time to pause it. Okay, hopefully you paused it and made your observations. So things you might have noticed about this are that there are some names at the top along the timeline. If we start on the left-hand side, gamma ray, maybe you've heard of that before if you're into like sci-fi stuff. X-ray, most of us have heard of. Ultraviolet light, UV, that's like what we get from the sun. You may have heard of like UV protection or sunscreen that's, UV, 30 UV or whatever. So that's an energy from the sun. The visible light, infrared, maybe you've heard of like an infrared camera or something. And then microwave we've heard of, and radio we've obviously heard of. So that might be something you noticed. You may also have noticed that there's like the rainbow in there. You may have noticed that on one side it says shorter waves, higher frequency, higher energy, and on the other it's long waves, lower frequency, lower energy. And then you may have also noticed this kind of wave along the bottom where on one side it's really a lot moving and then on the other side it's kind of slow. So now let me explain the electromagnetic spectrum to you. You may have noticed some other things too. Those are just what kind of pops out at me. So the electromagnetic spectrum is basically a number line based on the amount of energy that there is. Okay. So in the electromagnetic spectrum, we're looking at energy. And light travels in waves. So we talked about how there are photons that are coming from a star. They are traveling through space and they're hitting your eyeball. And when those photons travel, they travel in waves, just like water. And depending on how much energy they have, they're going to travel at a different wavelength or a different frequency. So what I mean by that is if something has a lot of energy, it's really energetic, it's going to travel in these really fast waves like this. And if you look on the bottom wave there, it looks like it has more energy. It's like this. Those are the gamma rays. Notice that the picture is right below the words that it goes with. So if gamma rays are really energetic and they have a lot of energy, what are radio waves on the other side? They're kind of these like long, longer wavelength, lower energy. And to me, they look like they have lower energy. All right, so we know that these photons are traveling in these wavelengths. The wavelength is how long it is from the top of one to the top of the next. And it kind of makes sense. So the wavelength for radio, if you're looking on the right side of the picture, you can see that the wavelength is pretty long, right? It takes a long time to get from one top to the other top. On the gamma ray side, look how short that wavelength is. From one top to the next top is really, really small. So on the gamma ray side, we have a shorter wavelength, a higher frequency. So frequency just means like how many times does it happen in a certain amount of space. So you can tell that it goes up and down a lot in one little tiny space. So that's a high frequency versus a radio wave on the other side has like this big long frequency, low frequency. And then the gamma rays have higher energy and they look like they have higher energy. Look at those waves up and down versus a radio wave, which has much lower energy. So this is the electromagnetic spectrum. What's really important for us and for you to understand and for bringing it to stars is the visible part. So that's right in the middle. If we zoom in, those are where we see colors and where we can see light. So our eyes are specially adapted so that we can see those wavelengths and those frequencies. Our eyes, we can't see infrared waves because they are too long, and we can't see X-rays or gamma rays because they're too small. So when you see a color, what you are seeing is a wavelength. So red has a different wavelength than green, than yellow. Each color has its own wavelength. And when your brain registers that, you see the color that you're supposed to be seeing. Where was I going with that? Okay, so if we zoom in on the visible spectrum, it's just a little tiny piece of this whole electromagnetic spectrum, and we pull it out. Which side is red on? Is it on the long wavelength, lower frequency, lower energy side? Or is it on the other side by gamma rays where there's a lot of energy? Well, if you're looking at it, then you see that it has a long wavelength, low frequency, and low energy. So the color red actually has a lower energy. And if you were to take that wave and keep making it longer, eventually it would turn into infrared. On the other side, we have purple. So purple and blue, they are on the shorter wavelength, higher frequency, higher energy side. So when you see photons that are blue and purple, it's a higher energy. Okay, that is all of the new information today. So just to remind you all of the things we talked about, we started by talking about what is light. And we learned that light is basically a photon. It's a piece of energy that is flying from the source through the air and is hitting your eyeball. And when you see it, you say, oh, look, light. So we learned about that. Then we learned about light years as a distance and how far away some stuff is from us. And that it can take millions of years for a photon to fly through the air and hit your eyeball. And after we talked about that, I'm just going to look at my notes again because I forgot. It was so long ago. Then we talked about the electromagnetic spectrum. And we talked about how in there are different types of waves with different wavelengths and different amounts of energy, and how we can only see a tiny little piece of that. We're going to be talking about the electromagnetic spectrum a lot more, and you're going to do more practice with it tomorrow. And then if you are coming to school, you will actually get to do a lab talking about the electromagnetic spectrum. So expect more work on this. If you didn't quite understand it, that's okay, because we're going to do more practice with it. But if you're really lost, then let's find a time to meet so that we can get it figured out. Okay. Make sure that you finish up your note sheet, please, and submit it through Google Classroom. Bye, everybody.